So it's a great pleasure then to introduce Chris Heunen for the third lecture on pointless topology and universal joints. Chris, your stage.
Thank you very much, and welcome back everybody for a new exciting week of tensor topology. So just to summarize quickly what we did last week, because of course nobody forgot, but nevertheless, we talked about monoidal categories, and we saw that inside monoidal categories, actually let me bring that up. We looked at certain morphisms into the tensor unit called central idempotents. We asked that they satisfy all these pictorial equations that you see on this slide. And we call them central idempotents. We saw that they behave a lot like open subsets of some sort of base space. We saw that they form a semilattice in general, but not really a topological space. So today what we're going to do is see how we can upgrade that to an actual open subset of a topological space. And at the end of today, last week we spoke about morphisms can be supported on one of these central idempotents. So that means they restrict to these central idempotents. They sort of live only above that open subset that's modeled by that central idempotent. So last week, because we only had a meet semilattice of central idempotents, we had to contend ourselves with the support of a map being the set of all central idempotents to which it restricts. So we're sort of approximating from above, the real open that we're interested in. But today we'll be able to talk about, once we upgrade from a meet semilattice to an actual topological space, we're able to talk about the support of a morphism. Like there's one central idempotent over which the morphism lives, so to speak. Okay, so that's the plan for today. But when I say topological space, I have to be a bit more precise because I really mean pointless topological space. The monoidal category that somebody gave us that we're interested in has these central idempotents, behave like open sets, but we really only have the open sets. We have nothing like points. So first I'm going to talk to you about pointless topology, or locale theory as it's called. And I'm going to hit you straight with a definition at first. So we say a locale or a frame is a complete lattice satisfying this infinite distributive law there. So complete lattice means it has a partial order on it. This partial order allows least upper bounds or suprema of arbitrary subsets. So any subset in this lattice whatsoever has an ideal point lying just above it, if you like. And it satisfies this infinitary distributive law there, which says that U meet a supremum of V's is the same as a supremum of the U meet all the V's. Now, this definition is of a locale or a frame. So as objects, locales and frames are the exact same thing. There are these kinds of lattices, but they have a different kind of interpretation. So when I say locale, I sort of mean the topological aspect, and we'll see this in more detail in a minute. And when I say frame, I mean more like the algebraic aspect. Like, for example, a meet semilattice is more algebraic. It's only about the meet. There's a third aspect that I'll sometimes refer to, but that we don't really go into detail of, which is a logical aspect. You can think of a locale or a frame equivalently as a complete Heiting algebra. So there you think of the elements not so much as open subsets of some sort, but you think of them as propositions. And you think of the meet as conjunctions. So some proposition is true and the other proposition is true. And then the fact that this complete algebra is a Heiting algebra means that it has something like an implication in this thought bubble on the right. So that is saying that if I have three propositions U, V, and W, I can derive conclusion W from the hypothesis U and V exactly when I can derive from hypothesis U alone the fact that V implies W. That's sort of a definition of what implies the connective of implication means. And it turns out that being a complete Heiting algebra is the exact same thing as being a frame, but it comes with this different connotation. And this connotation expresses itself in the morphisms. So as objects, these three things are the same, locales and frames and Heiting algebras, but they form different categories because we choose different morphisms between them. If we're talking about frames, these are the algebraic aspect of these complete lattices, then it stands to reason to ask for functions between lattices that preserve the algebraic operations. So specifically, a frame homomorphism is a function that preserves f of u meet v is the same as FU and V. And it preserves suprema. So the supremum of F of a bunch of UI is the same as the F of the supremum of the UI. So it's a frame homomorphism, and you can have a category called frames. You can take the opposite category of that, and we'll call it locales. So the objects are locales, and a map from one locale to another is a frame homomorphism in the other direction.
Cool.
You can also take complete Atlantic algebra morphisms if you like, and you will get a sort of logical category, but let's forget about that for now. Okay, fine, this is a nice definition. Why would we be interested in? Why does that make sense? And the main reason we're interested in is this. If you start with a topological space, you can look at its topology. So its set of open subspaces, subsets. That's not just a collection of subsets. It is what's called a frame, right? As we just saw, because by definition of topology, it has to be closed under finite intersections or meets and arbitrary unions or suprema. And of course, this infinite distributive law that I just showed you is just saying that finitary meets distribute over arbitrary unions, which is just true for sets. So any topology is a frame in that sense. But how about the morphisms? If you start with two topological spaces, X and Y, and a continuous map between them, then you will get a map between the two topologies. It should go in the other direction from OY to OX. Because what it means to be a continuous function, literally, by definition, is that the inverse image of an open subset is open. So if I take an open subset of Y, and I'll call it V, its inverse image is an open subset of X. And inverse images preserve finite intersections and arbitrary unions, and hence it's a frame morphism, but it goes in the other direction. So continuous function from X to Y gives a frame homomorphism from OY to OX, and hence a locale morphism from OX to OY again. So all in all, that gives us a functor from the category of topological spaces and continuous functions to the category of locale and locale morphisms. And that's our main source of locales. That's why we're interested in locales. There exists other kinds of locales in some sense, but we're not going to bother too much with them. Now, the main difference between locales and spaces, as we were saying, is locales, we only care about the opens. We've never spoken about the points. It's just the frame of opens, the topology itself, with no underlying carrying set of points. But we can try and sort of reconstruct the points as follows. So if we start in a topological space X, a point of that space is the same thing as a morphism from the singleton space with the discrete topology into the given space. Right? So that's a continuous function. It picks out for that element of the singleton space, it picks out a single point of X, and it's always continuous. As we just saw, a morphism between topological spaces is the same, induces a morphism between the locales. So a point of a topological space X is the same thing as a locale morphism from O of 1 to O of X. And by definition, locale morphisms are just frame morphism the other direction. So a point of a topological space X is the same thing as a frame morphism from OX to O1. And we know exactly what O1 is, because the singleton space has exactly two opens, the empty set and the singleton itself. And that's just 0, 1, the Boolean algebra 0, 1, if you like. And now if we pick apart what it means to be a frame morphism, we can look at, for example, the inverse image of the top element of this two-element Boolean algebra. That's the dashed part of this Hasse diagram of X that I drew there, the open subsets of X. If you look at all the things that get mapped to 1, that completely determines this morphism. And it's what's called a completely prime filter. It's a subset P of opens that satisfies 4 things. It's non-empty. It's upward closed in the sense that if it sends something to 1, then all the larger things also have to go to 1. Or differently said, if in an actual topological space, a point is in an open, then it's certainly also in all larger opens. It is down directed because if a point of the space is in 2 open subsets U and V, then it's certainly also in their intersection, which is again an open subset. And it's what's called completely prime, which means that if the supremum of a bunch of opens is in the completely prime filter, then at least one of them has to be in the completely prime filter. So if you think about this in terms of points and opens for a topological space, it means a point is in a union of open subsets if it is in at least one of the open subsets. So this way we can think about pointless topology, if you like, by just looking at the locale of opens, forgetting about the points. We can sort of reconstruct the points if they're there by looking at the completely prime filters of the locale. So the points of a locale, if you give me a locale, I can look at its points. They will form some sort of set, and I can topologize that set and turn it into topological space by demanding that, by declaring that basic opens are going to be things of this form, where I fix an open of the locale, and I say a basic open are things of all the things in the completely prime filter that contain that open. That will put a topology on the set of points, and that space is called a completely prime spectrum of the locale. So if you start with a topological space, you can build a locale out of it by taking this curly O functor, and you can go back the way by taking a locale and looking at its completely prime spectrum, its sort of set of points in this topology, and that will be a topological space. And in fact, that's a functor, because if you have a locale map, then you can take a map between the completely prime spectra like this. So a locale map F, let's say, goes from L to M, means it's a frame map going from M to L. That will write OF inverse. Now, if you give me a completely prime filter in L, I can make a completely prime filter in M out of that by applying that frame map to it. That turns out to be a continuous function. In fact, that's sort of precisely why I chose this topology on the set of points. So this gives a functor back from locales to topological spaces. And in fact, if you've seen adjunctions, that's the adjoint of the taking opens functor. So there's this connection between topological spaces with points and locales without points, at least where there's no points in the definition.
Chris, I have a quick question, if you don't mind.
Yeah, of course.
Are all the topological spaces you hit in the essential image of the spectrum functor sober?
No, that's not the case. You can undress this adjunction to an equivalence by demanding that the locales are what's called spatial and the topological spaces are what's called sober. That's a kind of, it's a bit like a separation condition.
Okay, so it's spatial locales that give you sober spaces.
Yes.
Then.
Yeah, that's right.
Okay, thank you.
But we will only deal with spatial locales in this lecture, I think, if I say correctly, yes. So you can just think about the locale as the open subset of a topological space, if you like.
Okay, thank you.
All right, so I told you this story for complete lattices now, where we have arbitrary joins, arbitrary suprema, but you can play the exact same game with if you only have finite suprema. So in that case, we don't have a frame, but we have a distributive lattice, something that has binary joins, binary meets, and where the joins distribute over the meets. And you can do the same thing, except then you don't look at completely prime filters, but at prime filters. So the condition about suprema is just weakened to binary joins. To be precise, if you have a distributive lattice L, a prime filter of it is still a subset, it's still up close, it's still down directed, but it's now prime, and this is where the word comes from, in the sense that if a join of two opens is in the filter, then one of them must be in the filter. And again, that means if you start with a distributive lattice, we can build a topological space out of it by taking its prime filters. It's called the prime spectrum, this space. Again, I can put a topology on it to make it a topological space. Again, there's an adjunction between the two. And what's sort of interesting, and we'll use implicitly somewhere in the next lecture, I think, is that these basic open sets that I put on the prime filters to make them into a topological space, they're going to be compact subsets. So in some sense, that means it's good enough to do things finitely. So I just want to mention that, but I think this is the main picture to keep in mind. Think of a locale as the opens of a topological space. Now we're going to be specifically interested in a very simple type of locales, namely locales that look a lot like one-point spaces. So I'll remind you that the goal of the whole course is to build up towards the sheaf representation theorem that says something like, you give me a monoidal category, and I will prove that it's always a sheaf over some base space of smaller monoidal categories, and not just smaller, but as small as they can be in some sense. They can be decomposed further. That's the notion of very simple locale I want to talk about now. So specifically, I'm going to call a locale sublocal if the following property happens. If the join of two opens U or V is the whole thing, is 1, then either U had to already be everything or V already had to be everything. So if you think about that in the logical kind of way, where you think of the locale as a complete Heiting algebra, this is what's called a disjunction property, because it says if I have a proof of the proposition U or V, then it must be the case that I have a proof for U, or I must have a proof for V. So this is a very constructive interpretation of the connective or, if you like. It's called a disjunction property. Some systems have it, some systems don't. So typically, similarly, a locale can be some locales are sublocal, some locales are not. That's sort of the finite tree version. The infinite tree version is the following. A locale is called local if this property holds. If a supremum of a bunch of elements is 1, so if you can cover the whole space with opens, then already one of the opens must be 1. And this is think about it for a minute. If you can cover the whole space with opens, then one of the opens must already be the whole space. So in that sense, the whole space can't be very big. If you think about that logically, that's what's called the existence property, because it says that if I have a proof of the proposition, there exists an I such that Ui holds, then it must be the case that I already have a proof for Ui for some I. Right? So if you have a proof of an existential property, you must have a proof of one of the things. So that's when a locale is called local. So a locale is local sort of when it's very small, if you like. So to try and explain the sense in which a locale can be very small, a local locale, let's go back to topological spaces because we have lots of intuition for them. So this is a notion that comes from point set topology. It's not one that you might have heard before, but nevertheless. A topological space is said to have a focal point, little x, if every net in the space whatsoever converges to that point. So in some sense, that one point sort of determines everything that happens in the space, determines the whole topology. And another way of saying that is a point x is a focal point exactly when its only open neighborhood is the whole space. There's no smaller neighborhood around the point that isn't everything. X is really, the smallest open neighborhood of x is everything. And it turns out that this definition of local that we had on the previous slide, this one, the locale is local if and only if the space has a focal point. This turns out to be an equivalence. So if you give me a topological space, it has a focal point if and only if its locale of opens is local. So we think about these kinds of spaces as tiny, tiny spaces because they are a lot like a one-point space, where there's like one generic point. There could be more than one focal point, but they will be indistinguishable in the topological sense. So there is some sort of one generic point somewhere in the space, and it determines everything there is to know about the space. But that doesn't mean the space has to be a singleton, right? There could be more points. Here's an example of such a thing on the bottom right in red. If you think about the natural numbers, and I put what's called the Alexandrov topology on it. So I say that the open sets are exactly the subsets that are up closed. So if some number is in it, then all larger numbers also have to be in the open set. And I try to indicate them by the, the red bubbles. In here, the space, the element 0 is a focal point of that topological space. Because, you know, if you just look at this picture, look at the point 0, what open neighborhoods does it have? Well, it's only contained in, you know, the largest red bubble of all, which is everything. So its only open neighborhood is the whole space. So in that sense, this space, you know, is not a singleton, but it is still very small in that the point 0 sort of determines everything about the topology. Okay, now I've talked a bit about topology and pointless topology. Now I want to start connecting it back to monoidal categories. I'm going to put, just like we had a distributive lattice as a meet semilattice with some extra nice property, a frame is a meet semilattice with some extra nice property. I'm going to say similar definitions for monoidal categories that say something like the central subunits have nice structure. And then later on, we will see that any monoidal category sort of embeds into one of these with nice structure. So we can pretend that this nice structure always exists. Now I say any monoidal category, but I'm slightly lying. I'm going to need from now on that all monoidal categories inside are stiff in the sense that's on this slide. And what that's saying is that intuitively, before I go into the definition, it's saying that we talked about central idempotents as they're some sort of open subsets of some base space, and they form a meet semilattice. They come with some notion of meet, right? The tensor product is somewhat like intersection for them. But in any category whatsoever, there is already an existing notion of intersection or meet of sub-objects, and that's given by pullback. So what this property of stiffness is going to ask is that the two notions coincide. So more specifically, if I take an arbitrary object A, then the functor tensoring with A, I wanted to preserve sub-objects in that sense. I wanted to send meets of central idempotents to meets of sub-objects. So you should think about it that way intuitively. Technically, what it says is that this gray square on the left is a pullback. So if you have two central idempotents U and V and an arbitrary object A, then you can look at the map from A times A tensor V into A and the map from A tensor U into A by just forgetting about the U and the V. Now I know I can complete the square by looking at the meet of U and V by putting at the other corner of the square A tensor U tensor V. I can sort of forget the U and the V in the other way and the square will commute. But I demand that this is actually a pullback square. But you know, A tensor U tensor V is, in the categorical sense, the meet of the sub-objects A tensor V and A tensor U. If you look at that in pictures, that's a picture on the right. You start with an arbitrary object A that just keeps existing all the time, and two central idempotents U and V. I can either forget about V first and then U, or I can forget about U first and then V. Those two things are always equal, but I want these two to be the two sides of a pullback square. Now, the reason I was lying to you before, that is not any arbitrary monoidal category, is that all categories that I know of, all monoidal categories are stiff. I don't know of a single example that is not stiff. You can probably build some sort of free monstrosity, but I don't know of any naturally occurring monoidal category that's not stiff. Nevertheless, this is the notion of stiff. So that's sort of saying that intersection of central idempotents correspond to intersection of sub-objects. Now we're going to upgrade this notion of intersections of behavior of central idempotents to behavior of sub-objects in the larger category. To cooperation with a tensor product in the larger category in two ways. First, in a finite way, and then in an infinite way. Sort of like a distributive lattice has finite joints, and a frame or locale has infinite suprema. So the first one here is the finite tree version. It says a monoidal category has universal finite joins if two things. First, the nullary case. I wanted to have an initial object such that tensoring any object with that initial object is still an initial object. Second thing is a binary case. I want the semilattice of central idempotents to have binary joins in such a way that it cooperates with the tensor of the larger category. And by cooperates, I mean the similar sort of thing as on the last slide, that tensoring with A, the functor tensoring with A preserves these kinds of joins. That now means this gray square that I drew there is not only a pullback, but also a push out. So what is the gray square? Again, we have an object A and two central idempotents U and V. I can go from A tensor U tensor V, forget the U, go into AV, or if I forget the V, go into AU. So that's two sides of the pullback square. And I've asked that central idempotents have joins. So there's also something called U join V. I can tensor A with that. And I can go from U into U join V and go from V into U join V. I want this square to commute, be a pullback and be a push out. So it's sort of saying that the functor A tensor blank preserves joins. Immediate consequence of this is that if a monodal category has universal finite joins, then certainly its central idempotents are going to be a distributive lattice. Right? That's sort of part of the definition. Monodal category has universal finite joins exactly when the central idempotents form a distributive lattice in a way that cooperates with the tensor product in the larger setting. So of all the examples we looked at last week, lots of them have universal finite joins. For example, if you start with a semilattice and regard it as a monodal category, it is always going to be stiff. It will have universal finite joins exactly when it is a distributive lattice. What else do we have? The category of Hilbert modules over C naught X for a locally compact Hausdorff space X will always have universal finite joins. The category set will always have universal finite joins. The category of sheaves over a topological space, set valued sheaves, will always have universal finite joins. In effect, any topos will have universal finite joins. And in fact, any sort of monoidal extensive category will have universal finite joins. If you look at the category of modules over a bialgebra, that will have universal finite joins exactly when the central idempotents form a distributive lattice. In other words, when the central idempotents of the bialgebra form a distributive lattice. So many of the examples that we've seen already have this finitary nice property. Now let's move to the infinitary version. I will say a monodal category has universal joins, not finite, but arbitrary universal joins. If, first of all, the central idempotents have arbitrary suprema, and the same sort of thing as we did before, I want the functor A tensor blank to preserve these joins. So now I can't phrase it as a push-out square because there's more than two of them, but it's kind of a wide push-out, if you like, or a co-limit in general. Namely, I want the picture on the left here, where nothing happens to A and a single UI goes into a join of UIs. I want that to be the co-limit of the following diagram. The diagram consists of objects A tensor UI. I do nothing to the A, and I go from UI to UJ exactly when UI is smaller or equal than UJ. That forms a diagram, and I want the picture on the left to be the co-limit of that diagram. For any set of central idempotents you might pick, as long as it's closed under intersection. And if you like, we can always close it under intersection. So basically for any set of central idempotents. So again, this is sort of saying that the functor A tensor blank preserves suprema. And again, immediately from the definition, a category has universal joins exactly when it implies that its central idempotents form not just a mean semilattice, not just a distributive lattice, but in fact a frame or a locale. And again, most of the examples we looked at already have this extra nice property, namely a semilattice regarded as a monodal category has universal joins exactly when it is a frame. Category of Hilbert modules has universal finite joins. Category of sets has universal finite joins. Categories of sheaves over set valued sheaves have universal finite joins. Any topos has universal joins actually. And if you look at modules over a bialgebra over a field, that has universal joins exactly when the central idempotents of the bialgebra themselves form a frame. Okay, so these are three properties: stiff, finite universal joins, and universal joins, let's say monodal categories are, basic, nice, and extra nice, if you like. Why are these? So why do I think about these kinds of things as extra nice? Because I can sort of paste things together using central idempotence. I can derive something about two morphisms, for example, as in this lemma that we'll talk about in a minute. I can reduce a property of morphisms to a property of that morphism restricted to a central idempotence. More precisely, if you pick a bunch of central idempotents, they could be finite, they could not be, in a monodal category that has universal joins, that has universal finite joins in general, and if you want more than finally many central idempotents, then you have to insist that there are universal joins. And anyway, if you pick a bunch of central idempotents whose join is 1, that cover everything, then you can prove two things. You can check that two morphisms are equal, two parallel morphisms are equal, by just checking that their tensor product, with each of the individual central idempotents are equal. So you can sort of check locally among elements of the cover that two morphisms are equal globally. And similarly, you can check that a morphism is an isomorphism just by checking that its restriction to each of the covering central idempotents is an isomorphism itself. And then the technology sort of lets you paste the inverses together in a sense. And I think to digest all the definitions, because I think last time I went a bit too fast, to digest all these definitions about universal finite joins and things, it's good if you have a little try and think about proving property number 1. How would you do that? If I give you two morphisms f and g, the left to right direction, of course, is obvious. So let's look at the right to left direction. I promise you that f tensor ui equals g tensor ui, and I tell you that the join of all the ui is 1. How would you prove that f equals g? Then what you do is you go back to the definition of universal finite joins, which basically says that this gray square is a push-out. Now this is a square of two central idempotents, but of course we can make it into a finite number of central idempotents if we like, or even on the next slide, an arbitrary y push-out. Now if I put, hang on, I'm going to try swapping screen share things. Let's see if I can do that. So if I draw the square that we have here, the definition was that this is a push-out. Now I have a map f and a map g from A to B. I want them to be equal. So what I can do is I can put f tensor u here and f tensor v here. I have assumed that u join v is 1. So in other words, this is just a tensor I is just a. And the push-out property says there's a unique map here. And we know it has, well, we don't know that it has to be f yet, but f does make this thing commute. But I know also by assumption that f tensor each of the covering elements is equal to g tensor each of the covering elements. So I can do the same thing for g. And because there's a unique mediating map here, that means f has to equal g. So it's sort of straight from the definition that you can check when morphisms are equal. Hang on, if I stop sharing here, reshare this. All right, so that's the first part of this morphism. You can check when two morphisms are equal. In general, you can check algebraic properties of morphisms by checking that they hold locally on the parts of a cover. So that's why we're interested in these kinds of universal join properties. Another way we're interested in that, another way these universal join properties make life easier is last time we had to talk about the support of a morphism in a monoidal category as the whole set of all central idempotents that it restricts to. But now, if we have universal joins, we can just take the union or the joint, the supremum of this whole set and end up with a single central idempotent. We can now say, I can define this sub-function that takes a morphism and assigns to it sort of the largest central idempotent, the largest open, outside of which f does not restrict to it. So this is now the support of the morphism. This is like the largest open subset on which it lives. And again, this has some universal property. It's a universal version of support in the sense that it is a function from this, sorry, it's a functor from this category C less equal to its central idempotence of C, such that any other functor f that turns a morphism in C into an element of a locale must factor through it, as we saw last time, but now it's a single central idempotent. And it still satisfies all these support datum axioms. For example, the support of a composition is contained in the intersection of the supports. And similarly, the support of a tensor product is contained in the intersection of the supports. So now we can talk about support of morphisms and objects by just a single central idempotence. All right. Now, so that's why we like universal join properties. For the rest of the lecture, what I'm going to do is I'm going to start with one of these stiff monoidal categories. And remember, stiffness is a very, very weak property. And I'm going to upgrade this category into one that has these nice universal support properties. I'm going to do this in a free way. But to be more precise about what I mean about this, I have to talk a bit about functors. I've tried to push them sort of under the tablecloth for now, but now we really have to talk about them. So in general, if you have just a category, you can talk two categories, C and D. A functor from the one to the other is like a structure preserving assignment of things from the one to the other. It sends objects in C to objects in D, and it sends morphisms in C to morphisms of the corresponding type in D. Such a way that identities go to identities and compositions go to compositions. And you can put all of these together into a large category called cat, where the objects are categories and the morphisms are functors. But we're not just interested in categories, we're interested in various monoidal kinds of categories. So I'm going to have to ask some more properties of these functors. First of all, I'm going to ask that the functors we work with are monoidal. So now C and D are not just categories, but monoidal categories. And I'm going to ask that the functor sort of preserves the tensor product, in the sense that if you have any two objects, A and B, I can apply F to them and then take a tensor product. Or I can first take the tensor product A tensor B and then apply F to them. I want there to exist a canonical morphism phi AB from the first thing I described to the second thing. It's not necessarily an isomorphism, just a morphism, so a lax monoidal functor. That satisfies some coherence conditions that I'll talk about in a minute. And similarly, for the nullary case, I want the tensor unit of C to be mapped to the tensor unit of D. And this time, I do want this map to be an isomorphism. So I want a bunch of these maps for all objects A and B. I want them to work together in the sense that they're natural, which is the gray diagram on the bottom right, which says that I can do a morphism to A and a morphism to B and C and then map them over. Or I can first map them over and then do the morphisms on the other side. And it has to be coherent, just as these monoidal categories we talked about have lots of coherence conditions and a coherence theorem. So that means these morphisms, these families of morphisms phi have to cooperate with all the other coherence isomorphisms, like the associator in the bottom left diagram and the uniters in the middle diagrams. So if you take these kinds of maps between monoidal categories, we'll call that thing mondcat. Now we're going to go a bit further. What are the appropriate morphisms between stiff monoidal categories? Well, I'm going to ask that they preserve the half braiding, in the sense that if you start with a half braiding in C, you can apply F to that and use the lax monoidal structure of F to get something like a half braiding in C and D, but it might not be defined everywhere. I want it to be extendable to a half braiding on all of D. And secondly, I'm going to ask that these lax maps phi AU, that first tensor A and U together and then map them over, or first apply F to both and then tensor them together, that those things are isomorphisms. If you're in a braided monoidal category, that is automatically going to be true already, this half braiding extension. So that I will call a morphism of stiff monoidal categories. If it preserves the half braiding and tensoring A with a central idempotent is the phi maps on there are isomorphisms, are invertible. From that, it follows that if you give me such a morphism of stiff monoidal categories, that induces a function between their central idempotents. Namely, if you give me a central idempotent U in C, I will turn it into a central idempotent in D as follows. First, you have to just apply F to it. So now you have something from FU to FI. And then I apply this phi I thing to get the FI into an I, as it should be. So you can turn central idempotents in C into central idempotents in D. And this is going to be a semi-lattice morphism if additionally it behaves well with respect to these half braidings, in the sense of these two equations at the bottom. And again, if you're in a braided monoidal category, that will happen automatically. It's always true. You don't need to worry about it. So that's morphisms of stiff monoidal categories. They preserve central idempotents in a nice way. And the final thing I'm going to ask is, what's the appropriate notion for monoidal categories that have universal joins, finite or not? Well, they should of course be monoidal morphisms of stiff monoidal categories, but also I wanted to preserve these joins. And that's all. I'm just going to ask that they preserve these joins, and that will be the category mondcat J or mondcat Fj. Right, so now we have various very large categories of monoidal categories. The goal for the rest of the lecture, is you give me a stiff monoidal category. I'm going to add freely universal joins to it. So you give me C. I'm going to construct a monoidal category with universal joins or finite universal joins. I'll call DC, such that first of all C embeds into it in a stiff way. And if you have any stiff functor out of C going into a monoidal category with universal joins, it must factor through D of C. All right, so we're going to sort of complete C with universal joins. And the idea is going to be the same as you always do in completions. For example, if you want to complete the rationals to the reals, what you do is you sort of formally add the things. So you're sort of missing the limits of Cauchy sequences. And what you do is you just define objects in the reals to be Cauchy sequences when you quotient out when two things give the same limit. It's the same sort of thing here. I want to add formally joins of central idempotents. So I'm just going to take as objects in my completion formally these things that I'm interested in. So objects in the new category are going to be pairs of two things. First, an object in the old category. But second thing is together with a down-closed subset of central idempotents. Right, so objects in the new category are just objects in the old category together with a down-closed subset of central idempotents. The interesting thing is the morphisms I'm going to choose in the new category. If you have two of these objects in a new category, so that means two objects A and B in the old category and two subsets of central idempotents in the old category, a map between them in the new category is going to be a family of things from A tensor U to B, where U ranges over all the central idempotents in the domain object, such that these morphisms restrict to some element of the chosen family of central idempotents in the codomain object. And furthermore, they sort of cooperate in the way that if U is below U prime on the domain side, then I want the eta u to be related to the eta u prime by sort of precomposing with this inclusion of u into u prime. Okay. So I'll repeat. Objects in a new category are pairs of things. Morphisms between them are families of morphisms from AU to B that all restrict to some V in the codomain and that are compatible with the order in the domain. The identity on an object A, D, A just has components where you keep the A intact and forget about the U. That's a fine morphism. And composition of two such morphism is sort of done central idempotent wise, if you like. So you give me eta and zeta. I have to produce something that goes from A tensor U to C for all the U's in D. What do I do? Well, I'm promised that eta U factors through something in E. So I first do eta U, I factor it through something in E, and then I do the zeta for that thing in C, in E, as on the bottom right picture there. You can prove that this is well defined and it is an actual category. This composition is associative and the identities satisfy the identity law. So this is the way we start with a stiff monodal category. We build a new category out of it. And now for the next 5 or 10 minutes, I'm going to progressively show you some structure of this new category and prove that it does what I advertised it to do. Let me look at the time. I think I'll skip proving that it is a well-defined category. But it's not just a well-defined category, it's in fact a monoidal category. Because I can also give you the tensor product of two objects and two morphisms in a new category. If you give me two objects in a new category, so that means two objects in the old category A1 and A2, I know how to take their tensor product, and two downclosed subsets D1 and D2 of central idempotence in the old category, that I will combine by just taking their intersection, which will still be a downclosed subset of central idempotence. So that's the way I take the tensor product of objects. The nullary case of that is I have to tell you what the tensor unit is in a new category. Well, I just take the tensor unit in the old category together with which downclosed subset of central idempotence. Just take all of them. So the downset of 1, if you like. And then I have to tell you how to take the tensor product of morphisms. So suppose we had a bunch of objects A1, A2, B1, B2 as on the first displayed equation here, and morphisms F1 and F2 between them, sorry, eta1 and eta2 between them. How do I take the tensor product? Well, I have to now produce a morphism, a family of morphisms from A1 tensor A2, tensor some U that is in D1 and in D2, to B1 tensor B2. And I will just take the obvious thing you can do, the picture on the bottom right here. So you feed the A1 and the A2 into the two families you already have, and you copy the U around, and you know that the U is in both D1 and D2, so I can feed it to eta1 and eta2. Okay, so that's how I define tensor product. You have to prove that this is well defined, but you can do that. All the associators and uniters and things you can inherit from downstairs, from the old category. And that way you can prove that the new thing is in fact a well-defined monoidal category. And not just that, we built it in such a way that the old category embeds into the new category. Namely, if you take an object in the old category, I send it to an object in a new category by just attaching to it all the central idempotence. This object sort of lives everywhere, if you like. And if you give me a morphism in the old category, I send it to a morphism in a new category by building a family of things of the form A tensor U to B. I just do F to the A and I forget about the U. So in a sense, this family is all sort of restrictions of F. F sort of lived everywhere. So in that way, you can check that this is a functor. It's in fact a full and faithful functor. So it's an embedding of C into its completion. And you can check that it's a strict monoidal functor. So it preserves tensor products on the nose. Okay, great. So we started with an old category, built a new one, into which the new one embeds, into which the old one embeds. So what? What's so great about this new one? So I promised you this new one is going to have universal joins. So we better figure out what the central idempotents are in the new one. Now I claim the central idempotents in the new category are in correspondence with the down-closed subsets of central idempotents in the old category. Namely, if you give me a down-closed subset of central idempotents in the old category, D, I can map it to a central idempotent in a new category that looks like the thing in the statement on the lemma on the left. It's a map into the tensor unit from D, I. What is that morphism? Well, you just forget the U, where U ranges over D. So in this sense, sort of D, the D part of an object in a new category in a free way says sort of where the object lives. That's the claim. Now to prove this claim, I have to prove various things to you. First of all, that the map I described is actually well defined. So the thing I defined on the left is actually a central idempotent in the new category. That's fairly straightforward and mainly a matter of chasing definitions. I put them on this slide, but I don't think it's very useful to go through them. I have to prove that this is a semi-lattice morphism, if you like, or a partial order, a monotone map. And I have to prove that it's injective and surjective. All that is fairly straightforward, and we're not going to do that now. Mainly, maybe one tricky part is you have to pay attention to central idempotents are only unique up to isomorphism. So they're not just maps into the tensor unit. Two of them are identified when there's an isomorphism making the triangle commute. But other than that, it's relatively smooth sailing. Okay, so in the new category, we can identify what the central idempotents are, and they are sort of the free completion of central idempotents in the old one. In this precise sense, if you start with a meet semi-lattice and you look at all its down-closed subsets, that is going to be what's called a free frame on L. It is a frame because I can take suprema just literally taking unions. The union of a bunch of down-closed subsets is again a down-closed subset. It includes L itself because L embeds into there by looking at the principal downsets. And it is free in the sense of the triangle on the right here. If you have any semi-lattice map from L into any other frame F, then there's a unique map from the completion of L into F that takes a down-closed subset D, looks at what little f does to all of its elements, and then just takes the join of that in F. So in other words, taking down closed subsets is the free frame completion of a semi-lattice. And basically what we did on the past few slides is a similar thing, but sort of upgraded that to monoidal categories. So we've proved that if you start with a stiff monoidal category, out of that you can build a new category DC that has universal joins. And before I go on to describe the universal property, let me mention that I now took all down closed subset, that's like the infinite tree version, but we could equally well have talked about universal finite joins by not taking all down closed subset, but only the finitely generated ones. So the finite union of principal downsets. So now we have this embedding theorem, and this is its universal property, and this was the goal for today. If you start with a small stiff monoidal category, and C, and D is an arbitrary other monoidal category that has universal joins, and F is a morphism from C to D of stiff monoidal categories, then not only can I embed C into its completion, there will be a unique morphism F hat from the completion to D that will preserve, that's a morphism of monoidal category with finite, with universal joins. That makes this triangle commute. So any larger category that contains C that has universal joins sort of has to factor through this embedding. In that sense, D of C is the smallest thing containing C that has universal joins. So we sort of succeeded in formally adding universal joins to C and nothing else. A rigorous way of saying this is that all these categories I defined with mondcat S on the left, stiff monoidal categories and their maps, and mondcat J on the right, monoidal category with the universal joins and their morphisms on the right. There's an inclusion from the right into the left. This completion D is a left adjoint of that. Okay, this was the goal for the day. This is what we wanted to do. We can embed any stiff monodal category into one with universal joins. So let me summarize what we talked about. We started talking about locales, which is a way to talk about topology where you never ever mention points. You only work with the opens all the time. You can still reconstruct the points if you like by talking about the completely prime spectrum. And particularly we talked about local and sublocal locales, which are like generic one-point spaces. They're as close as the singleton space as you can be. Then we talked about a monoidal category having universal joins, which means the central idempoles don't just form a meet semilattice, but they have joins, so they form a locale in a way that respects tensor product. And finally, we improved this embedding theorem that says that any stiff monoidal category I can upgrade to one with finite joins. So for all intents and purposes, that means that I can pretend any stiff category has universal joins. I can always move to the completion if I like. So next time in the last lecture, we're going to put this embedding theorem to good use, because we're going to prove the sheaf representation theorem that I promised you a few times now. It says that any category with universal finite joins, I can represent as a smoothly varying bunch of local categories. But for that sheaf representation theorem, I really need the category to have universal finite joins, which is why we went through the whole thing of this embedding theorem. But for that, you have to wait till next time. For now, thank you very much for listening, and I'm happy to take questions.
Let's first of all thank Chris. I have an awful lot of echo. Can you guys hear me? I don't know, but first of all, let's thank Chris together. All right, are there questions?
Well, I have a question. Maybe you could show us an example of this using the bimodules. Bialgebra, modules over bialgebra. So what these joins are and what does this construction give you? Or maybe it's already complete. So
if you take modules over a bialgebra, that will have universal joins exactly when the central idempotents of the bialgebra form a frame. I don't think I haven't worked that out actually. So if you start with a bialgebra whose central idempotents do not yet form a frame, you can do this completion to them to make it into a frame. I haven't worked out what happens if you do that. Of course, you can do the formal thing. I can tell you what D of mod A looks like. But if you have that concrete category, some things might simplify, and I haven't looked at it. Sorry, I can't give you a good answer there.
Well, what do these joins look like if it is a frame? There's if Zi of A is already a frame.
I guess then you know that the intersection of two central idempotents is their multiplication. Mm-hmm. So I guess that means that the infinite intersection of an infinite bunch of them is, some sort of limit of finitary multiplications of each of them. And from the infinite intersections, you can probably find their infinite join. But one of the reasons I wanted to talk about this subject in this course, in this Atlantic Algebra Centre mini course, is because my background is not so strong on quantum groups and Hopf algebras. And I think this is one of the most interesting examples of this whole sheaf representation theorem that I haven't been able to work out myself. So I'd love some help with that, actually, because next time we'll talk about the sheaf theorem. It will sort of say that the representations of a quantum group, you can always see them as a sheaf varying over some base space. of other things. But the other things are no longer categories of modules of, sorry, categories of representations of quantum groups anymore. Because as far as I know, if A is a Hopf algebra and E is a central idempotent in there, E times A is no longer a Hopf algebra. It's something else. And I'd love to know what's going on there.
Certainly right about that. Further questions? Let me ask one. Can you guys hear me? Can you hear me, Chris?
Yes. Yes.
So the whole approach kind of gives preference to joints or unions over intersections. Some of the things look as if they could potentially be dualized. On the other hand, maybe I'm wrong about this too. So the question would be, to which extent can this be dualized? In other words, replacing intersections with unions and vice versa.
I think you could do the whole thing upside down if you like, but then instead of, you have to redefine central idempotent dually as well. So they're no longer maps into the tensor unit, they're maps out of the tensor unit.
Exactly.
And then their tensor product would be the join, I suppose. Actually, so there's some precedent for these central idempotents, namely Drinfeld and Boyarchenko looked at them. And they define it in as quotients of the tensor unit. They talk about open quotients and idempotent, no, not idempotent, but closed quotients, I think. And they do it dually. We decided to do it this way because then it matches up with a lot of theorems from Topos theory, from categories of sheaves, which are all about maps into the terminal object. Does that help?
Yeah, definitely answers my question. Thank you. Are there further questions? If that is not the case, we close for today. I will stop the recording now. Whoop. Stop.